novel Discrete transport. Authors are W.A. Gunarathna and H.M. Nasir. This presenting author, W.A. Gunarathna, is a lecturer at Department of Mathematics, Faculty of Engineering, General Surgeon Kotra, Defense University, Ratmalana. He has vast experience at past algorithm for discrete transform, numerical solution for fractional order differential equation, developing fast and robust algorithm for quadratic eigenvalues of the computation number theory and computational algebra. So,
Session Chair, ladies and gentlemen, good afternoon to us. As we know, discrete transforms such as discrete Fourier transforms, spherical harmonic transform, wavelets are being widely used in many scientific and technical applications, including engineering, biomedical engineering, signal processing, image processing, etc. Therefore, the notion of the discrete transform is very important in practical and theoretical setting. In this paper, we define the new discrete transforms. In order to define this, we have some inputs. What are the inputs? You could see n is a positive non-negative integer, and we have input sequence beta and also complex parameter. At the moment, we call it a complex parameter. And also w is equal to the power I 2 pi over n, which is an n root of the unity. Then we define our alpha is the output of our transform. It is a finite sequence. Each term in this finite sequence is given by alpha k p equal to finite sum j from 0 to n minus 1 sigma plus w to the power jk whole to the power p for all j to k from 0 to n minus 1. This is the one that we studied in this, we defined in this studies. You can see here the derivation of the DFT. You all know what is the discrete Fourier transforms. In the case where sigma equal to 0 and p equal to 1, our transform provides the discrete Fourier transform DFT. That is j from 0 to n minus 1 beta j double power jk. And also the efficient fast algorithm available, which is called the cool-to-key fast Fourier transform. Its complexity is n log n. These are the well-known factors. As we know, the discrete Fourier transform, the fundamental properties of the discrete Fourier transforms are linearity, periodicity, and inversions. Likewise, our transform also governs the properties of linearity and the periodicity. You can see here beta and the gamma are the input sequence. The linear combination is a beta plus by. The transform of that equal to a into transform of beta plus b into transform of gamma. We call on the point of mathematical, we call this is the linear operator. It's called the linear transformation. And also periodicity. Our output of the transform is an n periodicity. You could see there alpha k plus np equal alpha kb for all k from 0 to n minus 1. We call them n periodic sequence. And also knife computation, the direct computation of our algorithms, our transforms equal to matrix vector multiplication a into beta. Beta is our input sequence. To perform this matrix vector multiplication, we need at least compute the complexity of order p into the power 2. P for a fixed value of the p. Then for a large values of n, this compute the complexity become prohibitive. Right? Therefore, we also further developed a fast algorithm to compute our transform efficiently. This is the one we have developed certain theorems to develop the fast algorithm for the transforms, and also our transforms based on the fast Fourier transform FFT. Here also we have made some assumptions. N is divisible by p. That's the one we made here. Then the transform given by alpha k, we have put in our paper. This can be computed in n log n computer complexity. N log n computer complexity. and then this is the proposition in a mathematical term. And then the theorem 1, this is also we developed. This is of course the case where P equal to 2 in our transform. Then this transform also can be computed in a log n computer complexity. Here also the assumption is n must be divisible by 2. And also the theorem 2 also, this is the special case of the our general transform when P equal to 3. We also here proved that this transform also can be computed in a computer complexity of n log n. Here we have made the assumption, what is it? N must be divisible by 2 and 3. This assumption is coming due to the fact that we are using the fast Fourier transform. If you are going to use some other way, sometimes we don't need to do these kind of assumptions. Then we proved our general transforms can be computed in a log n computer complexity. These values of n provides that n must be divisible by all the positive integers from 2 to 3 minus 1. That is also assumption we have made. These are implementations. We can get our implementation. That's the theorem 1. Probably we can say the algorithm 1. The inputs are the sigma w and beta. Output should be our transform outputs. We got the outputs under 3 stages. In the stage 1, we calculate the C, as you can see. Stage 2, we calculate the fast Fourier transform of or discrete Fourier transform of 511, 512, and 522. And then we obtain the D11, D22, and D22. At the end, we have the output of the results. You can see ndt equals C plus the column vector D11 plus column vector D2, D2. This gives the output of the transforms. Similarly, we have implemented theorem 3, theorem 2, and the theorem 3. This and then we have written the MATLAB implementation of the algorithms and also theorems. These are the personal computer we have used for our purpose. Efficiency, to test the efficiency of the algorithms, we use the MATLAB C2 time. And to test the accuracy is tested with respect to the relative errors. We measure the relative error with respect to the maximum norm and with respect to the relative norm, with respect to infinite norm, R infinity. Here V is the output of the fast computation, V star is the output of the knife computation or direct computation. Then the numerical results we presented in the case where in part A sigma equal to 10 and the P equal to 2 and sigma equal to 10 and the P equal to 3. Right? And also the sequence beta is we randomly selected from the interval 0, 1 for the various values of n to test the efficiency and the accuracy. These are the results we got for the sigma equal to 10 and the P equal to. You could see my red color curve indicates C2 time for the knife computation. My blue color curve indicates the time for the fast computation. That's just above the time axis. You can see when for a large values of n, this gap is very high. Right? You can say this gap is very high. This says that the fast computation more efficient than the knife computation. You could see the similar results, similar relationships when the sigma equal to 10 and P equal to 3. And these are the relative errors we computed. My first column, the input size n, and the second column is maximum relative error and the R infinity with respect to relative error infinity norms. You could see there are errors coming varies from 10 to the power minus 20 into the 10 to the power minus 3. Both kinds of things are right. These are various points that change. So this actually says that the fast computation is also more accurate. Right? More accurate. If you go to the relative errors when sigma equal to 10 and the P equal to 3, you could see that he also related to errors where is from the 8 to the 10 to the power minus 12 to the 10 to the power minus base. These numerical results also confirm that the fast computation of our transform is more accurate at the theoretical numerical results. And also concluding remarks, you can see in this paper we define the new discrete transforms and also define the we define the fast algorithm for that also. And also accuracy and the efficiency of the fast algorithm were also numerically tested in the cases where p equal to 2 and the sigma equal to 10 and p equal to p equal to 2 and the 3 and the sigma equal to say last time must be a p equal to 3 and the sigma equal to 10. Then the and also the numerical computation were performed in MATLAB. And we identified the most important properties of this transform, linearity and the periodicity. However, the most important properties is the inverse formula for these transforms. It is yet to be determined. So we are working towards that, but our findings are not yet sufficient to present. Here also we develop on the theoretical aspect of our transforms. We haven't factored for any practical situation yet. We need to have what is the inverse of the transforms. It is yet to be determined. So with that, I would like to turn off my presentations. Thank you very much.
Any questions from audience?
What is the main purpose of this new DFT? Now, have you compared it with FFT?
No need to have the comparison.
No, but your comparison has no meaning if you compare with the normal. Normal, everyone knows it very slow.
Yeah.
So if you are comparing, DFT must be compared with FFT.
Yeah, that's right.
So, did you compare with FFT? Then how do you show that your results are more accurate? If you compare with the normal one and it takes thousands of iterations, you are not doing thousands of iterations. Therefore, you are saying it's faster. But if you take FFT, you have used FFT for a long time. Without comparing with FFT, which has an inverse transform.
Yeah.
If you don't have inverse transform, I can define any transform and it's very easy to transform. I will say the transform is twice my original. It will be very fast to transform.
Yeah, that's what we are considering exactly.
No, to me, unless you have defined what it can do, and if you can't define the inverse transform, then what is the purpose of this transform?
One thing is, I haven't, anyway I mentioned that we cannot determine the inverse transform.
No, you are not determining it. If you are not determining it,
it is yet to be determined.
then it is not done.
Yes.
This
This is
what I
the
am
concept of the transform we have.
If I define y is equal to 3x, it will be very much faster than doing any other transform.
Yeah.
But unless I can show that I can transform back, that transform has no meaning.
Up to now, but we can develop this one for further purposes.
No. Once you are developing, you can present it. Until that time, what are you really presenting? To me, I don't see anything that is. Well, you say you are not comparing with FFT.
Sir, the thing is that this cannot be compared with FFT. This is a new transform. How can you compare?
No, but FFT is something. No. Then what are you comparing with? You are not presenting any results. You are not comparing anything. And you cannot inverse transform. Then what are you presenting?
I compare with the direct transform.
No, direct transform, everyone knows it's very slow.
If the something is coming, the new, how to...
No, but that, you also know that there is something called FFT.
Yeah.
Then why didn't you compare with FFT? Because FFT is millions of times faster than
Exactly.
normal.
The FFT and our two transforms are two different things.
Yeah, I know. So then you must compare with that and show that your one is having an advantage.
Yes, up to now we so that this is...
Otherwise, no. There's a Rolls Royce and there's another car.
Yeah.
And then I say I'm not making a Rolls Royce and therefore I'm comparing this car with walking. To me there is no meaning.
I agree with you. What I say, mathematically I give the new concept of the new transforms. That's why I did
No, transform unless you have method of inverse transform, that's not a transform.
Yeah. But inverse is to be determined. That's why I.
No, then what I was saying is, until you can show how it can be, even you don't even have an idea of how it can be inverse transform.
Yes, what you are telling is I agree with you, but I cannot control something without being inverse, right? But that's a different point of view. I have seen this one through the mathematical point of view.
No, then
right?
you will at least show
Yeah.
a comparison with
Yes.
other similar methods like FFT.
That is a thing, right? Every mathematical theories are not the perfect things. Later on, people have improved it. That's the nature of the study of the mathematics, right?
Okay, then what is the purpose of this transform?
This is I gave the concepts.
For what purpose?
Once we have the inverse, sometimes we can apply it later on to some applications.
Future work, I think.
Yes,
we just compare with F2 and
Of course.
with your outcome. I got one word, novel discrete transform. This word novel. Okay, you have put your all the references 1965, 1977, 1997. You have to research recent article as well because
Yes.
you have reference only to old. Then if you get that word novel,
No, that is
not
right.
here.
FFT and
Yeah,
many other
yeah.
things are novel.
Yeah.
But you cannot compare with something that was there 20 years ago and say it's novel.
Yes,
Yes,
that's
yes,
true.
yes.
I say.
Yeah, because suppose if you put this type of word novel,
Yeah.
it is not that easy. Okay, then if you want to get novel word, you have to research all the articles, around 100 articles, and you will find at least this word is novel. Otherwise, it is hard to say this novel word. Okay. Any more questions from audience?
What is the expected application do you think in the future you have?
Probably, I think probably on the FFT and India apply in the secondary business. Sometimes we can apply.
No, in that case, you should compare with FFT. Well, if the application is going to be similar to FFT, you must compare with FFT, not with FFT.
Okay, thank you.
Thank you.
Ladies and gentlemen, that concludes the oral presentations of engineering session 4 on numerical simulation and optimization. On behalf of the organizing committee, I would like to take this opportunity to thank Dr. Nirosh Jayavira for chairing this session. May we have a good round of applause for Dr. Jayavira for chairing this session, please. Now I call upon Dr. Nirosh Jayavira to present certificates to the speakers of this session.